What if an object, currently hurtling through our solar system isn't just a rock, like a randomly wandering piece of space debris or an icy comet,
Hmm.
but something far more, well, deliberate, something with intent, maybe, or at least a design?
That's a provocative start.
Welcome to the deep dive. Today, we're going to embark on a truly remarkable, and for some, I think perhaps unsettling journey. We'll unpack a recent academic paper that presents this meticulously constructed hypothesis concerning the interstellar object designated 3I Atlas.
Right. And our mission on this deep dive, just to be really clear for you listening, it's not to prove or disprove the existence of alien technology.
Not at all. No.
Instead, we're committing to a thorough exploration of what the paper's authors themselves actually call the testable hypothesis.
Okay.
So this is a fascinating thought experiment, a scientific what if. It postulates 3I Atlas could indeed be a technological artifact, and maybe even more profoundly, it examines what the paper suggests about its potential intentions or future actions.
And it's vital to understand, isn't it, that the source paper explicitly states this. They say its authors are presenting this as a pedagogical exercise.
Exactly, a way to push the boundaries of scientific inquiry,
Mm.
even if its implications could lead to what they term, well, dire consequences.
That's a powerful disclaimer, isn't it? It really frames this whole discussion not as like a declaration, but as an invitation to, I guess, rigorous scientific imagination.
Hmm.
So the core question we're grappling with as we explore this really detailed analysis is precisely this. Could this enigmatic interstellar visitor actually be a piece of alien technology?
And if so,
And if so, what does this paper suggest about its possible next moves, its strategies within our solar system, or even perhaps its ultimate purpose for being here? Let's dive deep into the data and the deductions.
let's do it.
So let's begin our exploration by getting to know 3I Atlas itself. This isn't just any space rock. It was first observed on July 1st, 2025 by the Asteroid Terrestrial Impact Last Alert System, or ATLAS.
ATILAS, yeah. It's an observatory system designed specifically to detect objects that might pose a threat to Earth. The name feels almost poetic, given what we're talking about.
It does, and what makes 3I Atlas so significant immediately is that it's only the third interstellar object we've ever definitively detected passing through our solar system. Just the third one.
And that number third is highly relevant because it immediately draws comparisons to its predecessors. The most famous, of course, being Oumuamua, discovered back in 2017.
Right, Oumuamua, that caused quite a stir.
It really did. Oumuamua, even though it was only visible to our telescopes for, a fleeting 2 months, it ignited what quickly became a very public and, at times quite a bitter controversy within the scientific community. It displayed several anomalous features that astronomers are still intensely debating today.
Can you maybe elaborate on this anomalous features of Oumuamua? What exactly made it so controversial, and why is that context important for 3I Atlas now?
Certainly. Well, the primary anomaly with Oumuamua was its non-gravitational acceleration.
Meaning it sped up on its way out.
Exactly. The speeding up as it departed the sun, but without any observable cometary activity, no tail, no, ejected gas or dust that typically causes this kind of acceleration in comets.
Okay.
For natural comets, right, as they approach the sun, ice sublimates, turns into gas, and these jets of gas act like tiny thrusters, pushing the comet. Oumuamua just didn't show this. It was like watching a boat suddenly accelerate across the water with absolutely no visible engine or wake. It was weird.
Very strange.
This lack of outgassing led some prominent scientists to hypothesize it might actually be an artificial object, perhaps a light sail being pushed by solar radiation pressure.
Right, the light sail idea.
Yeah. And this ongoing debate about Oumuamua's artificiality, contentious as it still is, it sets a crucial precedent. It sort of primes the scientific mind to consider that maybe, just maybe, not every interstellar visitor is a natural celestial body. It makes the current discussion about 3I Atlas not entirely unprecedented, even if it remains deeply provocative.
That context about Oumuamua is really essential, I think. It highlights that the scientific community, while typically, very cautious, does engage with these extraordinary possibilities when the data presents itself in unusual ways. And to analyze 3I Atlas's complex trajectory and its potential implications, the paper we're discussing today uses some incredibly sophisticated computational tools. Specifically, they employed an interplanetary mission design software called OITS.
Optimum interplanetary trajectory software, yeah.
So this isn't just sketching ideas on a napkin. This is like serious high-precision orbital mechanics at play here.
Precisely. The power of tools like OITES allows for incredibly detailed simulations. You can explore this vast array of possibilities for an object's path, its potential maneuvers.
Right.
And it's the results of this rigorous analysis that truly illuminate the ambiguous nature of 3 Alice, which in turn is what compels the paper's authors to even open the door to the technological artifact hypothesis.
But
The paper, very systematically, first examines the two primary natural explanations for 3 Alice. But then, it meticulously details why both of these natural scenarios present pretty significant difficulties when you weigh them against the current observational data.
So let's break down those natural explanations then. What's the first common assumption about what an interstellar object like this might be, and why does the paper argue it doesn't quite fit?
Okay, the first and often simplest possibility is that 3 Alice is just a typical asteroid, basically a large chunk of rock floating through space.
Makes sense.
Now, if we assume a standard albedo for an asteroid, which is just its reflectivity, right, around 0.05, meaning it reflects about 5% of the light that hits it,
Uh-huh.
then 3 Iodilis would need to be roughly 20 kilometers in diameter to explain its observed brightness.
20 kilometers, that's pretty big.
That's considerable, yeah.
Mm.
And here's where the paper raises a major flag. Objects of this specific size passing through our solar system from interstellar space should be many orders of magnitude rarer than something like Oumuamua, which was maybe only a few hundred meters long.
Many orders of magnitude rare. Can you unpack that a bit? What does that mean for our understanding? Is it just incredibly unlikely, or does it actually challenge our statistical models of, like, how many big rocks are floating out there?
It implies an exceedingly low probability event. I mean, think about it. Even smaller interstellar objects are thought to be rare. We've only found 3.
Right.
So if we're seeing a 20-kilometer asteroid as only the third known interstellar visitor, it suggests something statistically very, very unusual. It means either our current understanding of the distribution of large free-floating asteroids in interstellar space is dramatically off, or something else is at play. To put it into perspective, maybe, it would be like flipping a coin and getting heads, I don't know, a dozen times in a row. It's possible, but it definitely starts to make you wonder if the coin is weighted, right?
Definitely raises eyebrows.
The sheer statistical improbability for a natural asteroid of that enormous size to just randomly show up as one of our first few detections is a significant point of contention for this natural explanation.
Okay, so if it's statistically improbable to be an asteroid that big, what's the other natural explanation? And why does that one also seem to fall short? We have had interstellar comets before, right? Like 2I Borisov.
We have, absolutely. Borisov was clearly a comet. So the second natural explanation is that 3I Atlas is a comet. Now, if it were a comet, as it approaches the sun, it should typically begin to outgas. It should form a discernible fuzzy coma, that cloud of gas and dust around its nucleus, and exhibit other signs of cometary activity, maybe like a tail.
And we're not seeing that.
Well, here's the thing. The paper explicitly states a critical observational fact. There's been absolutely no sign from spectroscopic analysis of cometary activity on 3I Atlas to date.
Okay, what exactly would spectroscopic analysis show us if it was a comet acting normally?
So spectroscopy breaks down the light from an object into its constituent wavelengths, right? It's like a chemical fingerprint. If 3I Atlas were a comet, we'd expect to see spectral lines indicating the presence of water vapor, maybe carbon monoxide, or other volatile compounds evaporating off its surface as it gets warmer.
And there's just nothing.
The complete absence of these specific spectral signatures is highly unusual for a cometary body this close to the sun. Now, to be fair, some initial observations have shown what maybe looks like a faint fuzziness around 3 Atlas.
Okay.
But the paper acknowledges that this observation is pretty inconclusive. It's really hard to differentiate a genuine cometary coma from just, image smearing or blur caused by the object's rapid motion across the telescope's field of view during long exposures.
Right. Tricky to be sure.
So we're left with this persistent dilemma. It's statistically really improbable to be an asteroid of its implied size, and it shows no clear, unambiguous signs of being an active comet.
And this ambiguity itself, as you said, is the very crack in the wall.
Exactly. It's what opens the door, scientifically speaking, to considering the technological artifact hypothesis. Neither common natural explanation fully fits the current observations, which compels scientists, or at least these authors, to consider, well, alternatives.
This is where the narrative really starts to twist, isn't it? When we move beyond trying to fit 3i Atlas into our existing boxes for natural objects and start looking at its actual behavior, its trajectory,
Hmm.
we uncover what the paper meticulously details as a series of anomalous characteristics.
Hmm.
These aren't just random observations. When you piece them together, they begin to form this pattern that, for some, starts to look uncannily like evidence for intelligent design, for technology.
And the first, and perhaps most striking piece of evidence, lies in 3i Atlas's orbital plane. Okay, so we know it's on a hyperbolic trajectory.
Meaning it's just passing through, not staying.
Right. It has enough velocity to escape the sun's gravity after passing through, never to return. It also possesses a non-zero speed way out at infinite distance, estimated around 60 kilometers per second. That's incredibly fast. Far faster than any human-made probe has ever achieved for interstellar travel on its own.
60 kilometers a second. Wow.
But here's the extremely unusual feature the paper highlights. Its orbital plane is tilted only slightly from the ecliptic.
And the ecliptic, just to remind everyone, is that relatively flat plane where all the major planets in our solar system orbit the sun.
Exactly. So 3 Atlas's inclination is only about 5 degrees from the ecliptic.
Yeah.
And it's retrograde, meaning it's orbiting in the opposite direction to our planets. Its inclination is technically 175.11 degrees.
And the statistical improbability of that alignment, especially being retrograde but so close to the ecliptic plane, is truly staggering, right? The paper calculates the likelihood for such a precise alignment of its orbital angular momentum vector with Earth's, essentially, its path through space to be only about 0.2%.
0.2%. That's like 1 chance in 500.
Wow.
It's not strictly impossible for a natural object, of course, but it certainly stands out as exceptionally rare. A real coincidence, if it is one.
And the paper goes on to detail the potential benefits, let's say, this particular statistically improbable alignment offers to, well, an extraterrestrial intelligence, an ETI.
Right. A low ecliptic tilt, particularly when the object is still far from the sun, would allow an ETI to precisely determine the orbits and the masses of our solar system's planets.
How would they do that?
Through what are called astrometric measurements. Essentially, extremely precise observations of how the planets move and how their gravity subtly influences each other over time. This kind of reconnaissance would be absolutely crucial for an ETI looking to prepare an optimal approach strategy to our solar system.
Okay.
In essence, the paper argues it grants them access to our planet with relative impunity, allowing them to gather vital intelligence without immediately drawing too much attention.
From our perspective as humans, that makes perfect, if slightly unsettling sense, doesn't it? If an ETI wanted to observe us carefully before revealing itself, this would be a pretty smart way to approach. But for us, it's almost infuriatingly inconvenient. The paper points out that missions to 3i Atlas would have been much easier had the interstellar object been traveling in the ecliptic plane prograde.
Meaning moving in the same direction and plane as our planets.
Right. Because this makes any human intercept mission extremely challenging, if not impossible, with chemical rockets. The velocity difference is huge. The inclination is difficult.
It's almost as if it's designed to be hard for us to catch or even scrutinize up close, which, leads us directly to the next striking characteristic the paper highlights. It's uncanny planetary proximity.
Ah, yes. This part was jaw-dropping.
The paper presents what I found to be a truly shocking statistic. As 3 Atlas makes its journey through our system, it approaches Venus incredibly closely at 0.65 astronomical units. That's roughly 97 million kilometers.
Okay.
It gets even closer to Mars at 0.19 astronomical units, about 28 million kilometers.
Wow, that's close for Mars.
And it also swings remarkably close to Jupiter at 0.36 astronomical units, or about 54 million kilometers. The paper emphasizes that it approaches all 3 of these planets particularly close.
And the methodology the paper uses to assess this is quite clever, isn't it? They basically said, okay, let's assume 3IA teals could have entered the solar system at any random time.
Right.
And then they calculated the pure statistical probability that it would just coincidentally align its trajectory to make these incredibly close approaches to 3 different major planets. It's a way of testing that coincidence factor.
And the results, frankly, are astonishing. The overall probability for all 3 planets to align in such a way for these close encounters, purely by chance, is calculated to be less than or equal to 0.005%.
Yeah. To really grasp that, it's less than 5 chances in 100,000. It's like picking one specific person out of a packed football stadium 3 times in a row, purely by luck.
Okay, that's vanishingly small. And the paper explicitly emphasizes this is an upper bound on the probability, meaning the true probability of this happening naturally is likely even lower. This incredibly low probability is a significant statistical anchor for the technological hypothesis. It really forces you to ask, is this just an incredibly improbable roll of the cosmic dice, or is there something more deliberate going on here?
So it's on this super inconvenient orbit for us, perfectly aligned for them, maybe, and it happens to swing by 3 planets incredibly closely. But the anomalies don't stop there, do they? The paper highlights what it calls solar obscuration, a potential veil for maneuvers. Tell us about this timing aspect.
Indeed. So 3I Atlas is set to reach its closest point to the Sun, its perihelion, on October 29th, 2025.
Okay, coming up relatively soon then.
Yes. At that point, it will be at a distance of 1.35 astronomical units from the Sun, slightly further out than Earth's orbit. But here's the critical detail. At this precise time, it will be totally obscured from the Earth by the Sun.
Completely hidden.
Completely hidden, meaning from our vantage point here on Earth, 3I Atlas will be directly behind the Sun, making it absolutely impossible to observe with our telescopes. The paper calculates the likelihood of this specific solar elongation, basically its angular distance from the Sun as seen from Earth being less than 30 degrees, effectively putting it behind the solar glare as only about 7%, another low probability event.
But why is that specific timing so significant? I mean, the sun's a big object. Isn't it just bound to pass behind it eventually from our perspective?
The significance lies in a core concept of advanced spacecraft maneuvers, particularly what's known as the reverse solar O-berth maneuver.
Reverse O-berth.
Okay, this isn't just a random event. The paper argues it's an optimal high-thrust strategy for interstellar spacecraft to brake and stay bound to the Sun. The basic principle of the O-berth effect is that a rocket engine generates more useful energy, more change in velocity when it fires at high speed, deep within a gravity well.
Right, like pushing a swing at the bottom of its arc.
Exactly. You give the biggest boost when it's moving fastest. Similarly, for a spacecraft, imparting thrust at perihelion when it's moving at its maximum orbital speed relative to the Sun allows it to maximize the change in its kinetic energy. In this case, a reverse O-berth would mean firing engines to slow down, potentially allowing it to decelerate enough to enter a more bound orbit within the solar system instead of just flying through.
And the implication?
The implication here is profound. Any maneuvers of this kind would be obscured from Earth observation. It would allow a, quote, surprise arrival on Earth to be conducted, or at least a significant change in trajectory to be performed completely covertly. It's the perfect blind spot for a dramatic shift in plans.
Okay, that's a bit chilling. And it gets even more challenging for us to track, right? The paper also points out what they call a hidden approach, almost as if it's designed to evade early detection from the start. Its apparent direction of origin, its incoming radiant, was from the direction of the Galactic Center.
Yeah, this is a subtle but very important point. The Galactic Center is, to put it mildly, a particularly bright region of the sky from our perspective.
Lots of stars. Dust.
Exactly. It's teeming with stars, dust, and gas, making it a very crowded and luminous background for astronomical observations. As the paper notes, this inherent brightness made the object particularly difficult to discern by Earth-based telescopes, which in turn rendering it less conducive to early detection. It's like trying to spot a dim, single firefly in the middle of Times Square at night rather than against a dark, empty field.
Makes sense. Harder to pick out.
Much harder.
And here's the really critical missed opportunity from humanity's perspective that the paper highlights. Had 3I Atlas been discovered earlier, significantly earlier, the paper argues that humanity could have mounted an intercept mission.
We could have sent our own probes, maybe, to get a closer look, analyze its composition, its structure, its origin. Figure out what it actually is.
But by the time 3I Atlas was actually detected, that option was simply out of the question. The math just didn't work anymore with current propulsion.
Right. And the optimal launch date for a human intercept mission to 3I Atlas was incredibly over a year ago, specifically July 9, 2024.
Over a year before it was even discovered.
Exactly. It's almost as if its arrival timing and direction were precisely calibrated to be just too late for us to react proactively with an intercept. The insights here are really piling up orbital convenience for them, observational inconvenience for us, and a trajectory that inherently limits our ability to respond directly.
Okay, let's unpack this further then. If all these anomalous characteristics aren't just a string of truly incredible, statistically improbable coincidences, then what does this behavior suggest about 3 Atlas's potential intentions or strategies? We hear words like dire consequences and surprise arrival. Is this paper actually suggesting, well, are aliens about to attack?
That's the logical and, yeah, unsettling question that arises when you start seriously considering these possibilities. The paper approaches the idea of malign intent, with scientific caution, of course, but it certainly explores the potential for it within a broader discussion of what kinds of maneuvers 3I could execute based on its trajectory.
Okay.
The first key indicator of, let's say, ease of action for 3I is its low delta V for intercepts.
And delta V, just quickly for our listeners, is that fundamental concept in spacecraft propulsion. It stands for change in velocity, and it's basically a measure of how much energy or propellant burn is needed for a spacecraft to perform a maneuver. Lower delta V means easier, more efficient.
Exactly right. So 3I has already passed Pluto. It's on track to pass quite close to Venus, Mars, and Jupiter, as we discussed.
Right.
The critical finding from the paper's calculations is that the AV needed by 3I to either A, intercept any of these planets, or B, send probes to them is remarkably low.
How low are we talking?
Let's put some numbers to this. For Venus, the delta V required for an intercept is less than 5 kilometers per second before April 2025, and it stays below 10 kilometers until late July 2025. For Mars, it also stays below 5 kilometers until the end of July 2025. And for Jupiter, the intercept delta V is consistently low, less than 5 kilometers, all the way up to November 2025.
So it's like it has all these incredibly easy, low-energy pathways to different planets in our solar system? But you mentioned Earth as an exception earlier.
Yes, that's a curious detail mentioned in the paper. For Earth, the intercept delta V is always calculated to be above 5 kilometers per second.
Any speculation why?
The paper sort of speculates that this might suggest 3I, if it is an ETI craft, has perhaps narrowed its intentions to planets in the sun's habitable zone, maybe excluding Earth for a direct high-speed intercept for some reason. Or maybe it suggests a different approach, perhaps a more subtle one, is intended for our planet. We don't know.
But 5 kilometers per second? What does that even mean in practical terms for an object like 3I? What kind of capability are we talking about here if it were to, say, launch something at one of those planets?
Well, the paper provides a very stark and I think relatable comparison. It states, a speed of 5 kilometers is about equivalent to the speed of an intercontinental ballistic missile, an ICBM.
Wow. Okay.
This analogy is powerful because it's a technology we understand. It implies that, assuming a similar means of propulsion, chemical, or even more advanced methods, the object 3I could quite easily release probes of the same size that would reach planets of interest.
So it could potentially deploy smaller objects at high speed.
That's the implication. While 5 kilometers might not sound like warp speed in the vastness of space, it's a velocity achievable with very powerful, potentially chemical propulsion systems capable of delivering a payload. This is really where the concern about malign intent, as the paper puts it, begins to emerge more concretely.
And the paper goes further, doesn't it? Making a very specific, testable prediction regarding this potential for intercept or release that makes it incredibly tangible, really brings it home.
It does. It's not just vague speculation. It states that the optimal arrival dates for such an intercept visit, either by the object itself or alternatively a probe or weapons sent by it, will be from 21st November 2025 to 5th December 2025.
That's this year, end of November, beginning of December.
Yes. A precise time frame, less than 5 months from now, that future observations can either confirm or refute. If something unusual does happen during this window, a detected arrival maybe, or some unexpected phenomenon, it would strongly support the hypothesis. And yes, the paper directly states, with typical scientific understatement, the intercept option would possibly indicate a malign intent.
Malign intent. It's important to clarify, right? That doesn't necessarily mean like an immediate overt attack on Earth.
Correct. It could mean deploying surveillance probes, perhaps disrupting communication networks, maybe testing defenses, or even simply demonstrating capabilities in a way that's clearly not benign. The possibilities are broad, but the core idea is non-friendly action.
Okay, so beyond just these potential high-speed intercepts, the paper also thoroughly explores scenarios involving those Oberth maneuvers and various rendezvous options. We touched on the reverse solar Oberth, but it's worth maybe reiterating the power of using gravity assists, especially from the big players.
Absolutely. The paper highlights that our Sun and Jupiter are, obviously, the two most massive bodies in the solar system. Therefore, their immense gravity wells permit a spacecraft to capitalize most on the Oberth effect, enabling a minimum EV requirement from the spacecraft's propulsion system. It's all about leveraging natural physics for maximum efficiency. Smart maneuvering.
So while a direct intercept of Earth implies maybe a more immediate, potentially aggressive goal, the paper also considers a less immediate, perhaps more insidious rendezvous with Earth option.
Yes, that scenario is indeed available to 3i Labs based on the orbital calculations. It would require a minimum rendezvous delta V around March 2026. And crucially, this would involve applying that delta V clandestinely, hidden from us at low perihelion and solar elongation, just as we discussed with the reverse solar Oberth timing.
And what would a rendezvous achieve?
Well, such a rendezvous could allow 3i Atlas to enter into an orbit around Earth, perhaps becoming a long-term satellite for extended observation, rather than just a fleeting flyby. This option implies a more drawn-out, possibly covert reconnaissance mission rather than immediate conflict, though it still falls under the umbrella of a non-natural, deliberate action.
Okay, but the really complex and perhaps even more telling scenario the paper outlines involves Jupiter, doesn't it? This is where the authors describe what sounds like a truly grand plan for 3ILS. A Jupiter-Oberth maneuver combined with something called aero capture. This sounds like a masterclass in space engineering.
It really is, and it demonstrates the incredible sophistication that would be implied if 3ILS is artificial. This detailed scenario posits that 3ILS would conduct a Jupiter-Oberth maneuver to precisely match velocities and effectively rendezvous with Jupiter. This would involve a two-stage thrust application. First, a burn to intercept Jupiter, then a second burn, or maybe a series of controlled maneuvers to slow down and settle into a Jupiter parking orbit.
And that takes a lot of energy.
A huge amount. The calculations show that a delta V of at least 20 kilometers over would be necessary upon arrival at Jupiter, assuming a very close perigove altitude, the closest point to Jupiter in its orbit. That's a massive change in velocity.
And then it uses aero capture, right, using Jupiter's actual atmosphere to brake and slow down into a highly elliptical Jupiter orbit, or AGO. That sounds incredibly difficult for any spacecraft, let alone something that might be 20 kilometers across.
It is indeed a highly sophisticated maneuver, but also potentially incredibly efficient. Aerocapture leverages the planet's atmosphere as a natural brake, saving immense amounts of propellant that would otherwise be needed for a purely propulsive slowdown.
Right, using the planet itself.
Exactly. The physics involved are fascinating and have to be precise. 3i Atlas would approach Jupiter with a hyperbolic excess velocity, basically, speed relative to Jupiter of about 65.59 kilometers per second. It's moving so fast that without intervention, it would just swing by and escape Jupiter's gravity.
Okay.
When it encounters Jupiter's atmosphere at around, say, 899 kilometers altitude, it would be moving at a staggering 88.33 kilometers per second. Its entry speed relative to the atmosphere itself would be about 75.6 kilometers per second.
That sounds intense.
It is. But the impressive part, and what highlights the object's potential engineering, is that the deceleration needed for a successful aerocapture would be, according to the paper's calculations, just 25 meters per second squared.
Only 25 meters along. That seems surprisingly gentle for those speeds.
It's a relatively gentle deceleration. Yeah, showing incredible control would be needed.
So how does that amount of force and the resulting heat compare to what we've done with human missions, like Apollo returning from the moon? Is this within the realm of known engineering principles?
The paper makes a fascinating and very informative comparison here. While the energy dissipation from this aerocapture maneuver would be about 7.01 kilowatts per square meter, which is certainly high, it's explicitly not the multi-megawatt levels experienced during an Apollo mission lunar re-entry to Earth.
Ah, okay. So less intense heat than Apollo re-entry.
Significantly less intense per unit area. Apollo re-entry generated immense heat, needing thick, ablative heat shields that basically vaporized to dissipate the energy. Furthermore, the total heat load on 3i Atlas for this maneuver, calculated as 6.64 megajoules per square meter, is much lower than the 426.5 megajoules per square meter experienced by Apollo.
What does that imply about the object itself?
It suggests that if 3i Atlas were a craft, it would need to be equipped with incredibly efficient and robust thermal protection systems, perhaps far beyond our current capabilities for very large objects, but not necessarily violating the known laws of physics. It speaks to highly advanced materials and design.
And once it's in orbit around Jupiter using this aerocapture, then what?
Then the paper suggests something even more extraordinary. Conceivably, 3i Atlas can interact with Jupiter's Galilean moons and magnetic field to maneuver without use of propellant.
Without propellant, how?
Possibly using electromagnetic interactions with Jupiter's powerful magnetic field, or carefully timed gravitational slingshots off the large moons like Ganymede or Callisto. This points to an incredibly advanced, resource-efficient technology, allowing for long-term operations within the Jovian system without needing to refuel constantly. It truly implies a highly capable and self-sufficient piece of technology.
Okay, so we've talked about these powerful high-thrust maneuvers, intercepts, oberth braking, aero capture, but what about continuous low-thrust maneuvers? Those are also often associated with highly advanced propulsion, like in science fiction. Does the paper address those possibilities?
It does, yes. And this is where the solar sail theory comes back into play, building on that concept of non-gravitational accelerations we mentioned with Oumuamua.
Right.
Using sophisticated software, the paper investigates the minimum overall magnitude of these subtle acceleration components, radial towards away from the sun, transverse along the orbit, and perpendicular to the orbital plane that 3I Atlas would need to achieve specific goals, like intercepting Mars or Jupiter using low thrust over time.
And what did they find?
The significant finding here is that the A1 radial component, which describes acceleration directly away from or towards the sun for a potential Jupiter intercept using low thrust, is positive. It's accelerating outwards from the sun.
And why is that specific direction important?
It's crucial because a positive radial acceleration, continuously imparted like that, strongly suggests this could be achieved by a photonic solar sail.
Yeah.
Pushed by sunlight.
A solar sail. That's a classic sci-fi concept, but it's also a real technology humanity is developing, isn't it? Albeit on a much smaller scale.
Exactly. We've flown small test sails.
Mm-hmm.
So what kind of solar sail would this imply for an object the size of 3I Atlas? How big and how light would it need to be?
Yeah.
Let's consider the magnitude needed for that low-thrust Jupiter intercept. The required non-gravitational acceleration would be about 5.85 to 10 astronomical units per day squared, normalized at 1 AU from the sun. That translates to about 1.17 millimeters per second squared. It's a tiny, tiny continuous push.
Okay.
To achieve this, assuming a perfectly reflective sail, its areal density, which is its mass per unit area, would need to be less than 7.8 grams per square meter.
And what does 7.8 grams per square meter actually mean in practical terms? Is that something we could theoretically build today?
Well, the paper points out that this areal density is typical of the areal density of sails humanity has developed, like JAXA's Icaros mission or the Planetary Society's Light Sail 2.
Really? So the material properties aren't completely out there?
In terms of mass per area, no, which is a fascinating convergence. For example, the paper calculates a sheet of material with a mass density similar to iron, about 7,800 kilograms per cubic meter, actually.
Okay. Dense like iron.
But with an extraordinary thinness of just 1 micrometer, 1/1,000,000th of a meter thick, would have that required areal density.
Wow, incredibly thin.
Now, if 3I Atlas were a circular sail with a radius of approximately 10 kilometers, which, remember, is the current estimate of its size if it's a non-cometary natural object,
Right.
it would still have a considerable mass of about 4.8 million kilograms.
Yeah.
And its lightness number, which is a key metric in solar sailing representing the ratio of force from solar radiation pressure to the force of gravity, would be calculated at 0.20. This indicates a highly efficient solar sail capable of significant propulsion just from sunlight.
But what if it's not a flat sail? That seems structurally challenging at 20 kilometers across. The paper also considers an alternative structure, right? Like a sphere for rigidity and symmetry. What materials would that imply?
Yes, the paper intelligently considers a spherical structure, which could potentially be more robust for interstellar travel or maneuvering. For this, researchers have proposed interstellar spherical sails made of incredibly lightweight yet strong materials, like multi-layer graphene, or this stuff called aerographite.
Graphene, okay.
Assuming multi-layer graphene, which had an incredibly low areal mass density, like 0.758 attokilograms per square meter, fantastically light.
Wow.
And to achieve 3I Atlas's observed low albedo, its dimness of 0.04, it would require at least 96 layers of this graphene.
96 layers.
Even then, a 10-kilometer radius outer layer alone would mass at least 91.4 tons. But the total mass for a hypothetical absorbing sail of that size, accounting for structure and everything, could be at most 1,160 tons, according to the paper's estimates.
Okay, around 1,000 tons. And what does that total mass imply about its potential contents or purpose, if it is a craft?
This is a crucial inference drawn in the paper. It implies that such a spherical structure, even at that relatively low mass for its size, can contain multiple internal layers to brace it against outside forces, as well as significant payload like subprobes and sensor equipment.
Ah, so it's not just an empty shell.
Exactly. It reinforces the idea of it being a highly engineered, complex craft rather than just a simple natural object. A 1,000-ton spacecraft, even one that's mostly sail, could carry an immense amount of scientific instruments, communication arrays, or indeed the probes or weapons that were mentioned in the intercept scenario. It suggests a substantial, potentially multifunctional alien spacecraft.
And to try and tie all of this together, in terms of potential motivation or strategy, the paper introduces a concept that's often explored in science fiction: covert reconnaissance of an inhabited star system. They even cite Stanislaw Lem's incredibly influential 1987 novel, Fiasco.
Yes, which was a really sharp critique of traditional SETI assumptions back then. It's a brilliant and frankly chilling parallel they draw. In Lem's novel, an Earth vehicle named Hermes approaches an inhabited star system. But to avoid detection or potentially hostile reaction, it adopts the guise of a parabolic comet.
It pretends to be a comet.
Yeah, it even has an artificial crust and ejects gases to meticulously mimic natural cometary phenomena. And then it uses close flybys of gas giants to decelerate and obscure its propulsive maneuvering, much like the Jupiter Oberth and the solar obscuration scenarios we just discussed for 3I Atlas.
So what was the motivation in the novel for Hermes to adopt this cautiously covert entry? Why be so sneaky?
In the book, it's key. It's due to observing possible hostile activities remotely spread across the target system before it even gets close. Hermes sees signs of conflict or danger from afar and decides a stealthy approach is much safer.
Okay, I see.
This provides a plausible, if deeply unsettling motive for 3I Atlas's seemingly anomalous behavior. It suggests it might not be planning a direct, immediate attack, but rather conducting a cautious, intelligent reconnaissance, perhaps informed by observations that preceded its entry into the inner solar system. It's a reminder that sometimes the most profound scientific hypotheses can find their roots, or at least some really illustrative parallels, in the realm of imaginative fiction.
So what does this all mean when we put it all together? We've got this truly incredible cascade of characteristics. An unusual orbital plane that seems almost engineered for observation, incredibly close planetary approaches that are statistically just off the charts improbable, that solar obscuration at perihelion perfectly timed for a reverse Oberth maneuver, a difficult-to-detect radiant coming from the bright Galactic Center, and the consistent calculation of low delta V needed for potential intercepts or rendezvous with various planets. But not Earth, interestingly.
Yes, the paper masterfully synthesizes all these points. And it acknowledges very scientifically that each of these characteristics, taken individually, could quite easily have been simple coincidence, even as, quote, extremely strange as that ostensibly appears.
Right. Any one of these things might be just weird luck.
Exactly. But the paper argues compellingly that, taken together, these data points form a robust case for a testable hypothesis, that 3I Atlas is indeed technological. It's the cumulative weight of all these anomalies that demands a second look, that pushes beyond just saying, oh, that's weird.
And this brings us to a really fundamental scientific nuance, doesn't it? The challenge of distinguishing between mere cosmic coincidence and actual intelligent intent. I mean, the human brain has a well-known propensity to see patterns in what is actually random scatter. It's a survival mechanism, maybe, but one that can definitely lead us astray in scientific inquiry.
Absolutely. That lies right at the heart of a crucial scientific dilemma. Is an outlier of a sample a consequence of expected random fluctuation? Or is there ultimately a sound reason for its observed discrepancy? Is it just noise, or is it signal? Yeah. And the sensible scientific answer, as the paper notes, hinges largely on the size of the sample we're analyzing. And as we keep saying, for interstellar objects, we have a sample size of only 3 Oumuamua, Borisov, and now 3I Atlas.
Just 3. That's not much to go on.
It's a tiny sample size, which therefore rendering an attempt to draw inferences from what is observed rather problematic. This is precisely why the authors maintain such a high degree of scientific impartiality, presenting this as a hypothesis to be tested, not as a definitive claim of alien visitation. It's really a call for more data, more observation.
So while we definitely can't definitively declare, okay, aliens are here, what can we do right now? The paper bravely lays out some clear, testable predictions, right? These are the crucial next steps.
Precisely. The key predictions that will either support or refute this hypothesis over the coming months and year include, first, the potential observation of a visitor to Earth around the end of November to the beginning of December 2025.
That specific window again.
That specific window. This could be 3I Atlas itself, making a close pass after its solar encounter, or maybe it could be a smaller probe, or Yes, even weapon released by 3ILS during its hidden maneuvers near the sun. This is a very specific, actionable prediction that astronomers worldwide will be keenly watching for.
And the second key prediction?
The second is the measurement of significant non-gravitational accelerations, meaning if 3ILS shows signs of actively thrusting or maneuvering beyond what gravity alone would dictate, especially that specific positive radial component that suggests a solar sail, that would be incredibly powerful evidence for technology at work.
And the good news is telescopes across the globe are currently trained on 3i Atlas, right? So they should show any anomalies indicative of technology in the coming months, allowing us to actually test these predictions.
That's the hope. Though, as the paper points out, these telltale signs may only become apparent when 3i Atlas has passed perihelion after late October 2025 and is no longer obscured by the sun from our vantage point. So we're kind of in a waiting game for the next few months.
Right.
And we really should strongly emphasize, as the paper itself does repeatedly, that this groundbreaking analysis is presented as largely a pedagogical exercise. It's a way to stimulate thought and rigorous scientific investigation into how we'd even detect something artificial if it showed up.
Yeah.
It offers interesting discoveries and strange serendipities, all of which are worthy of a record in the scientific literature, regardless of the ultimate conclusion about 3i Atlas itself.
And it's crucial to underscore the most likely outcome, isn't it? From a purely probabilistic scientific standpoint, given everything we currently understand about the cosmos.
Yes, the paper states very clearly that by far the most likely outcome will be that 3i Atlas is a completely natural interstellar object, probably a comet. Maybe an unusual one, maybe one that's run out of volatiles on its surface, but natural nonetheless. That has to be the default scientific position until or unless overwhelming evidence proves otherwise.
Absolutely. Assume natural until proven artificial.
But here's the true lasting value of this type of analysis, I think, regardless of 3i Atlas's actual nature. The profound impact it has on how we prepare for future discoveries.
How so?
Well, the calculations presented here are useful, even if the interstellar object ends up being a comet like 2I Borisov, because they could be applied to future detections of interstellar objects by the Vera C. Rubin Observatory over the coming decade.
Ah, the Rubin Observatory. That's going to be a game changer for finding these things, right?
A massive game changer. It's expected to come online soon, and it will revolutionize our ability to detect faint, fast-moving objects like interstellar visitors. It will likely discover hundreds, maybe even thousands, of interstellar interlopers over its survey lifetime.
Wow.
So this paper provides a robust, detailed framework, a checklist, almost, if you will, of what anomalous characteristics to look for, what calculations to perform, and what implications to consider when we encounter the next Oumuamua or 3i Atlas and the one after that. It's about building a scientific muscle, developing the tools to distinguish the truly extraordinary from the merely improbable or unusual.
And there you have it, another deep dive into the fascinating, sometimes bewildering world of scientific inquiry. We've extracted some truly intriguing nuggets of knowledge today, haven't we? Showing how a seemingly simple interstellar object can spark such profound and complex scientific thought, really pushing the very boundaries of what we consider possible. It forces us to confront the limits of coincidence and to meticulously examine patterns that might otherwise just be dismissed as noise.
It really does.
So, as 3 Atlas continues its silent, rapid journey through our solar system, we're left with a question to ponder, something for you to mull over in the coming months as we await more data. If it turns out, as most scientists probably still predict, to be an entirely natural object, perhaps just a very unusual comet, what does that then tell us about the incredible, improbable coincidences that can occur naturally in the vastness of the cosmos? And if, by some slim, tantalizing chance, it isn't natural, well, what prepared us more for such an encounter? The rigorous scientific curiosity to painstakingly consider such a testable hypothesis, even if it seemed outlandish at first, or the sci-fi stories that have long imagined such profound and potentially unsettling visits, preparing our minds perhaps for possibilities beyond the ordinary?
That's a great question to end on.
Keep watching the skies and keep asking questions.